Welcome to ScalaUA conference.
Or shall we wait a few minutes?
No. Let's start.
Yeah, let's start. Okay. So, yeah, can you all hear me? Also in the back?
Yeah.
Great. So, yeah, my name is Matthias and I want to talk a little about the good, the bad and the ugly in Scala Refactoring. So, yeah, before I start, maybe a few things about myself. I already told you my name. I'm living in Vienna where I work for a company called Irium, and I became involved with Scala and started contributing to Scala IDE around 2014. And yeah, since I very soon became quite annoyed with the poor refactoring support in Scala IDE, basically even the most trivial renames were failing almost all of the time and leaving me with broken code, I started to do something about this, and since then became one of the major contributors to the Scala Refactoring library. Having said that, you should note, however, that I'm doing this in my free time, so I'm not having a full-time paid job for doing this, so I can, in general, maybe afford to spend one person day a week on these open source activities. Yeah, so since I already mentioned it, maybe a few words on the Scala Refactoring library. I'm not sure if any one of you knows it. I guess maybe not. So the Scala Refactoring library is a library that implements refactorings for Scala in a platform or IDE independent way, and it's currently being used by Scala IDE and Enzyme to implement operations such as rename, move class, organize imports, extract method, and so on and so forth. So, yeah, you might have noticed that I did not mention IntelliJ as one of the users of the refactoring library. So before I continue, let me ask you a short question. Who of you is not using IntelliJ for Scala development? Is not using IntelliJ. Alright, so that's what I expected. But I'd still encourage you to stay in this talk, because the things I'm going to say will also be relevant to users of IntelliJ, and yeah, will maybe help you also to understand why, for example, the IntelliJ folks decided to basically implement their own Scala parser and typer instead of using stuff that's already out there, like the presentation compiler. Yeah, so having said that, let me give you a brief overview of my talk. So in the beginning, I want to tell you a bit about abstract syntax trees, since they are like the very basis of my talk. And after that, I will explain to you how these abstract syntax trees can be used to implement refactorings and how the refactoring library does this. And yeah, so in the end, I will talk a little about the very interesting ScalaMeta and ScalaFix projects, and I will end my presentation with an outlook into the future and, of course, a summary. So yeah, let's take a look at the abstract syntax trees and the presentation compiler. So, those of you who saw this 50 Shades of the Scala compiler talk today already heard about the Scala presentation compiler. So the Scala presentation compiler is like an interactive version of the Scala compiler. Everyone who has a normal Scala compiler somewhere on his hard drive also has the presentation compiler on his hard drive, because the presentation compiler lives in the same jar file, it's just under a different package. And since it's meant to be used for interactive usage, it's doesn't generate bytecode from your source file, but basically stops after type checking. And it can do things like code completions, and it can tell you in the type, for example, if you are in a source file and you are at a specific position and you want to know the type that corresponds to this position, then the Scala presentation compiler can tell you this type. And it's used by Scala IDE and Enzyme, but as you might have already heard, not used by IntelliJ. So let's take a closer look at abstract syntax trees. So abstract syntax trees are just tree-like structures that are used generally by compilers to represent source code, and so that you have like a more concrete example at hand. I've included as a very trivial function here on this slide. That's basically just an identity on the integers, and below you can see a little simplified abstract syntax tree that corresponds to this very small identity function. So at the very top you can see that this method is represented by a def node, and this def node then has several children, the one on the left side representing the name of our function, the one in the center, the wall-def node representing the argument of our function, and last but not least on the right side we have this ident node representing the body of our function. And of course then these nodes have children themselves, and so on and so forth. And I guess you can imagine that if we had any non-trivial piece of Scala code, that these trees are quite big, because this is just a rather trivial function and the tree already has like 8 nodes. So for any non-trivial piece of code, of course these trees are rather huge. And for those of you who are like interested into experimenting with them, in fact we can use the toolbox compiler that we also heard about in the presentation about 50 Shades of the Scala compiler. So the toolbox compiler basically allows you to compile random or arbitrary snippets of Scala code, and it's also shipped with the Scala compiler jar. And so here in this code example, you can see that we basically instantiate such a toolbox, and as soon as we have this toolbox, we can then parse. Can you see the mouse pointer moving? Yeah, I guess you can see that. We can then parse and type check random Scala code and convert it to a string. And normally, since the generated strings are rather large and contain lots of nested bracket expression, it's useful to use some kind of formatting tool so that you can actually make sense out of the strings that you get. But basically it's just possible in a few lines of Scala code to print out the abstract syntax trees for arbitrary snippets. Yeah, so please, if there are any questions, are there any questions so far? Yes? Maybe is there a microphone somewhere a second? Yes.
Any Scala construct is in abstract syntax tree. Also comments, for example, everything, meta information, something.
What do you mean by comments?
Comments in code.
Comments? No, that's actually a problem. Comments are not directly represented in the abstract syntax trees. And yeah, this is a very good question. And yeah, I will talk about more about this later. But it's a very good question. They are not represented.
Yes, because it's a part of API, I think, also documentation or something like conventions regarding parameters.
Well, the abstract syntax trees originally were created for they are meant to be used by the compiler, and the compiler wants ultimately to generate bytecode from them. So of course, for the compiler, commands are not really relevant. On the other hand side, for an IDE or a refactoring library, this is quite different. But I will come to that later. Thank you very much for the question. Any other questions? All right. So, yeah, then I want just to also look a bit on the individual nodes of these abstract syntax trees we've been talking. So here I have another small code example, and I've just highlighted this as the .hashcode call, and below you can see the abstract syntax tree that represents this hashed code invocation. And so this tree then has, as most tree nodes have, a type, a symbol, and a position. So in our special example, the type of our tree is just a function that has no arguments and generates an integer. That's what a hashcode method does. The symbol of our tree is the hashcode method of string. So the symbol is some kind of unique identifier that can be bound to a tree node. And then, of course, typically, if you have some source code, then these typically the tree represents some of the source code that you have written in the file. So the position tells you exactly where this source code sits. And what I've written here is, of course, just an arbitrary number, since this depends very much on the specific location of this particular tree. However, something that maybe should be noted at this stage is that none of these attributes, so neither the type nor the symbol nor the position is mandatory. So we have trees without types. Think about import statements, for example. An import statement doesn't naturally have a type. We have also trees without symbols. Think of an integer literal or a string constant. A string constant doesn't have a symbol associated with it because it stands for itself. And a little bit maybe surprisingly, there are also trees that don't have a position. But I won't talk about them too much now because they will be discussed later. But for the moment, I just want to say that trees without position typically are just compiler-generated trees that have no direct representation in the source code. Yeah, so now that we have a basic understanding of abstract syntax trees, let's take a brief look at the way these trees can be used to implement refactorings by the Scala Refactoring library. So this is like the original design. The Scala Refactoring library itself was created in 2009 by Mirko Stocker as part of his master's thesis. And yeah, the original design of the refactoring library was like this. So at first the presentation compiler is used to parse the source code that should be refactored into nice typed abstract syntax trees. Then these trees are analyzed, transformed according to the refactoring operation that you have selected. For example, a rename refactoring. And once these trees have been transformed, of course they have to be translated back into source code, because you as a user, you as someone who requested a refactoring from an IDE, you're not interested in a transformation on an abstract syntax tree, but you rather want your source code to be patched in a way that represents the refactoring operation that you selected. So there's this phase called tree printing that is responsible for doing this transformation back into source code, and as soon as this is done, the rest is rather straightforward. Then changes can be generated accordingly, and in the end consumed by an IDE to perform the refactoring for you. So, like from a high-level perspective, this looks quite nice, and I guess it's also the way it should be done. But if we look into the details, unfortunately this all gets quite ugly. And yeah, this brings us back to abstract syntax trees and to one of the questions we had at the beginning. One problem with abstract syntax trees when using them for refactorings is that they contain no layered information. So if you look at these three examples here, F1, F2 and F3, of course from a compiler standpoint, these three functions are identical since they are semantically identical and should also generate exactly the same bytecode. All of these functions just multiply every element of this sequence by 2. But yeah, for a refactoring library, of course, there's a difference between those functions. Because if you invoke a refactoring in your IDE, you don't want the IDE to mess with your code style or with your formatting rules. Another problem with abstract syntax trees, and this brings me to the trees without positions, are the sugarings. Most of you maybe know that for comprehensions in Scala are just syntactic sugar for map, flat map, filter, and for each. And unfortunately, at the time the refactoring library gets the abstract syntax trees from the presentation compiler, these desugarings have already been performed. So in the abstract syntax trees that come from the presentation compiler, there are no for comprehensions. There is just map, flat map, filter, and for each. And this is basically what I want to point out with this example here on the left. So just looking at the abstract syntax trees, the two functions F1 and F2 here on the left side are basically identical. Again, this might be fine if you just want to generate bytecode, but if you want to do a refactoring, of course this is annoying, because nobody wants a refactoring library to convert a for comprehension into map and flat map, or the other way around. It even gets uglier as soon as named and default arguments are involved, since again the compiler desugars them. So the abstract syntax tree, so if you look at this example here, we have this function g with two arguments, both of them having a default value of 0. And then we just, here in this function f2, we just call g using the default value for a and setting b to 2. But the abstract syntax tree we get from the presentation compiler actually looks more like the function f2, where we at first manually set a local value to b, then we manually set a local value a to the default value of the parameter a, and then we just call the function normally. And of course this also causes a lot of headaches to the refactoring library, since this basically forces the library to reparse parts of the source code to extract the otherwise missing information. Yeah, so generally I guess that this should give you an idea of why implementing refactorings based on the abstract syntax trees from the presentation compiler is a very hard thing to do, and especially these tree printing part I was talking about, this phase where after the trees have been transformed according to your refactoring, they are converted back into source code. This is the place where these problems hurt the most, but they are quite annoying in general, even in other phases. So, of course, there are alternative approaches. One approach, in fact, was taken by IntelliJ. So they decided to just parse and type Scala themselves, which I guess was a good decision, but of course as a consequence, you now have IntelliJ sometimes to not be in line with the Scala compiler, so you have IntelliJ saying that your code is not correct, while the Scala compiler thinks it's okay, or the other way around. So this is basically the reason for this. And another alternative to implement refactorings, or another technology that could be used instead to implement refactorings, is ScalaMeta. Just so that I have an impression, who of you has heard about ScalaMeta? Oh, okay, that's already somebody. So let me briefly introduce ScalaMeta in comparison to the abstract syntax trees from the Scala presentation compiler. There will be more in-depth presentations about ScalaMeta later. So I will mostly focus on the advantages that ScalaMeta has in comparison to the presentation, to the abstract syntax trees from the Scala presentation compiler. So, for those of you who haven't heard about it, ScalaMeta is like a meta-programming toolkit for Scala, and one of its killer features is like abstract syntax trees. But unlike the abstract syntax trees from the presentation compiler, they capture really every detail of your source code. So they capture commands, they capture the formatting. And another very nice thing is that the ScalaMeta API is independent of the Scala compiler API. So it's not that tightly coupled, and everyone who has worked with the Scala compiler API knows that it's not always very user-friendly. And so that's really a big plus, in my opinion. And also ScalaMeta has a very nice API itself. So let's do a quick abstract syntax tree comparison. So here we have again our identity function f on the integers that we already used to illustrate the abstract syntax trees from the Scala presentation compiler. And this time we have on the left side the abstract syntax tree as it is generated by ScalaMeta, and on the right side we have the abstract syntax tree that we already saw from the Scala presentation compiler. So I guess it's not a big surprise that these trees look quite similar, but I still find it interesting that also the ScalaMeta tree is smaller. It contains exactly the same information, so it's like, one could say maybe a little bit more intelligently structured. Another thing, another technology based on ScalaMeta that I think is very interesting, especially in regards to refactorings, is ScalaFix. ScalaFix is like a code rewrite tool that's based on ScalaMeta that can, if you want, do batch mode refactorings. And one of its main objectives is to help people migrating to Dotty, but you can also use it, like, for example, to organize imports. You can use it to rename, you can use it to add explicit type annotations to implicit values. And in fact, one could even imagine library authors, when they do some breaking API changes, to ship ScalaFix migration scripts with the library, so that then users of the library could just apply these migration scripts to have the refactorings performed for them automatically. I think this would really be a very, very nice thing, and would allow library authors to more aggressively evolve their APIs without hurting users too much. So I think as someone who has contributed a lot to the Scala refactoring library, I think that at the moment the most interesting thing to do actually would be to abandon the old Scala Refactoring library and try to implement interactive refactorings based on ScalaMeta. Ideally, we would have like an interactive model of ScalaFix that would allow us to do all the things that ScalaFix already does and will do in the future in a batch environment, also in an interactive environment. And I guess that if we had such a tool, that this would also be quite interesting for IntelliJ. So maybe in the end, all the Scala development environments could end up using exactly the same implementation. But of course, there are quite some challenges ahead for doing this. In fact, there might be, but I really can't say, a Google Summer of Code project working in this direction, but we'll see. Anyway, I would very much like to see this happening. Also, since I'm only doing this in my free time, I won't like do it alone, but I would really happily contribute if such a project finds more people willing to work on it. Yeah, in fact, this already brings me to the end of my talk. So, what do I want you to take away from this? So, hopefully, you now understand a little better what makes Scala tooling so complex and why it sometimes, in fact, has a hard time catching up with Java tooling. And hopefully you also now understood why the folks at IntelliJ choose to basically re-implement the most complicated part of the Scala compiler, namely the typer. But most importantly, I hope that this got you excited about ScalaMeta and ScalaFix. And so yeah, I really encourage you to listen to the 2 upcoming presentations about this very topic. Thank you very much. Yeah, so are there any questions?
Can you mention a good tool for Scala code obfuscation?
I'm sorry, no. actually, I'm trying rather the opposite. I'm trying to write tools to understand Scala code. Not really, no.
Out of the box.
Any other questions?
How fast this work? Faster than idea. This is work faster than idea.
You mean if the refactorings based on ScalaMeta, if they would work faster than the refactorings in IDEA? Yeah. That's something I really can't answer at this stage. And I also think that that IntelliJ does a lot of things when you perform a refactoring that go beyond the scope of a simple Scala refactoring, because IntelliJ also searches in, I don't know, configuration files and stuff.
Okay, thank you.
All right, anyone else? Another obfuscation tool?
I have many of these. Okay, a library for smaller improvements to code, something like automatic addition of some specific comments or something. Yes.
You mean in the
like style check, like Scala style or something like that?
Yes, small refactorings like a shared open source library, something like model structure, and you can plug in some improvements to your code. And code is analyzed using ScalaMeta, for example, or AST, and you can use improvements just by plugging a model. Something like this structure is considered for further development by Scala gurus.
Well, I mean, if you had this, I mean, basically, you can already implement your custom batch mode refactorings right now within the Scala Fix framework. If you want, of course, there are still some limitations, but people are working very hard.
Think about security, for example.
Yeah.
There are security coding guidelines for Java. Actually, for Scala, it can be automated, like a tool that automates secure coding for Scala, to some extent. Think of ASP top 10 problems.
That's something that could be imagined. I mean, it would be quite different from a refactoring library, but of course, I guess that ScalaMeta could be leveraged to do some security analysis of your code.
Just an idea.
Yeah.
Hey, so there's one more thing, speaking of linting and ScalaFix. Recently, just a couple of days ago, Olaf, ScalaFix's author, he implemented support for linters. So previously, ScalaFix infrastructure only supported rewritings. And now it also supports linters, which basically allow you to report messages and not perform any rewritings. So I think there's a lot of promising development in that direction. Thanks.
I would have a question.
Yes.
How easy would it be like to use these facilities for code generation? So I have experienced a lot of cases where it has been useful to parse code of some software, and I use like Perl most of the time, which is kind of okay if you format your code nicely, and then generate other code, and I save a ton of time with that. And if you have facilities like that actually understand the language and allow you to plug in, if it's kind of not taking half a year to write such a thing, then maybe that's the more natural approach.
Yeah, I think, I mean, I'm really not the expert on this. The expert on this is sitting right behind here because he's the original author on ScalaMeta, but I think, yes, of course, you could use it for code generation.
For example, I work in the company which use very hard code formatting standards, but I like to write code in my own way. Can I use your tool to to automatically convert between the styles?
Okay, it's not my tool, and what I was talking about at the end isn't even there. It's just like something I would love to be there. That's like an interactive version of Scala Fix. But I guess there's a Scala format already there that can do basically what you want already.
Okay, thank you.
And any milestones when you expect it to be ready to use?
It's done when it's done. I'm sorry. But as I said, a Scala Fix is already there and it's already usable. The thing I was talking about in the end is this interactive version, and there are some challenges, I guess. All right. So thank you very much.
You should always keep things as simple as possible, and use the abstraction, the least powerful abstraction for your problem, and only if the problem at hand turns out not to be solvable with this, you use the next next more complex solution.